Welcome to our second lesson in probability. In our previous chapter, chapter 8, we learned to distinguish between subjective, experimental, and theoretical probabilities. We became familiar with probability terminology and properties of probability. We used the complement formula to find probabilities, and we created tables to calculate expected values for real-world applications, including insurance and product warranties. In Chapter 9, we're going to learn about probabilities that include the word and or the word or. We're going to determine if two or more events are independent. We're going to find conditional probabilities and determine if two or more events are mutually exclusive. We'll start this lesson with independent events. In this chapter, we're going to be discussing two events. We're going to label these as Event A and Event B. Event A and B are considered independent when the outcome of Event A does not change the probability of Event B occurring. In this case, finding the probability of both A and B occurring is just this simple formula: multiply the probability of Event A times the probability of Event B. In example 1, suppose we flipped a coin and rolled a die. We want to know the probability of the coin landing on heads and rolling a 2 on the die. Since flipping a coin has no influence whatsoever on rolling the die, these are considered independent events. So we'll just use our simple multiplication rule, where the probability of heads and the probability of 2 would just be multiplied together, like this. So the probability of flipping heads on the coin is 1 out of 2 possible outcomes. Probability of rolling a 2, there's only 1 2 out of the 6 options. We can put it this way, and we would say that is simply 1 out of 12. You can leave it like that, or you can convert it to a decimal. For example 2, we're going to use Artie the artichoke. He has a drawer with 12 pairs of socks. 6 of those pairs are green, 8 t-shirts, 2 of which are green. If he randomly reaches in and pulls out a pair of socks and a t-shirt, what is the probability that both of those are going to be green? So I'm just going to write this slightly differently and just say the probability of both green. And since picking socks and picking shirts are not going to influence each other, again, the probability of, I'll put green socks this way, times the probability of green shirts will give us our formula. And then we just need to fill it in. So he has 12 pairs of socks, 6 are green. That really is 1/2, but I'll write 6 out of the 12 times the probability of the 2 t-shirts out of 8. Now you can multiply this or you can simplify it first. I'll go ahead and simplify it to 1/2 times 1/4, 2 times 4, so that is 1/8. A couple has 2 children. Find the probability that both children are girls. For this one, pause the video, try the problem, then come back and check your work. So for this, I could just write out probability of having 2 girls. And that would be the probability that the first child is a girl times the probability that the second child is also a girl. There's 1 out of 2 for the first child, 1 out of 2 for the second child, and that equals 1 out of 4 times you would expect 2 girls. For our final example of independent events, we're going to roll a pair of dice. We want to know the probability that the first die will land on an odd number and the second die lands on a 2. It's really important to realize that each die is independent of each other, and what happens on that first roll or that first die is not going to influence whatsoever happens with the second one. So we're going to go ahead and just write this out, that we get an odd number and we get a 2. So probability of the first one being odd times the probability of the second one being 2. So the probability of the first one, half of the rolls are odd. For the probability of 2, that is 1 out of 6, and that is going to be 1 out of 12 times we would expect that to happen. For this next section, we're going to work with conditional probability. Conditional probability is the probability of event B occurring given that event A has happened. We represent that with this special notation, probability of B given A. If A and B are dependent events, say so what happens with A will change the outcome of B, then what we need to do is multiply the probability of A, because that occurs first, and then the probability of B given that A has happened. Sometimes the wording of the problem just wants the second event. That's what's considered conditional probability. Sometimes you need to know the probability of both events. This is the AND probability. Read carefully. Make sure you know what they're asking you to find. Many times conditional probability involves something like a deck of cards, where you would draw one card and keep it, which is what changes the outcome of the second event. Then the second event would be drawing another card. When we have that, I've input this little picture here to help you with understanding the problem. For this first example of conditional probability, we want to know the probability that we draw 2 cards from a deck of cards at random and we get 2 aces. Note that you are not replacing the first card. So what happens on that second draw depends upon what happened on the first draw. So we'll start here with the probability that we get an ace on the first draw. Note the deck of cards here, and there are 4 aces out of 52 cards, and we can simplify that down to 1 out of 13. For the second part, we want to know the probability of getting an ace on the second draw, given that we got an ace on that first draw. Since we have taken an ace out of the deck, there are only 3 aces remaining, and there's only 51 cards. This actually simplifies down to 1 out of 17. Now we want the probability of an ace on the first draw times the probability of the ace on the second draw. So that is 1 out of 13 for the first draw times 1 out of 17 for that second draw, which gives me 1 out of 221 times we would actually get an ace first draw followed by an ace second draw. If you want to see that in decimals, we can divide that out, and it's going to be really small. It is actually about, I'll round it to 4 decimal places, 0.0045. Very unlikely that would happen. For this next example, we're going to go back to that two-way table of red car, not red car, and speeding ticket, no speeding ticket that we used in the last chapter. But this time we are going to use conditional probability. So it says, what is the probability that a randomly chosen person has a speeding ticket given that they have a red car? So we want the probability of a ticket but it's not out of everybody. Instead, we already know it is given that they do have that red car. So for this, we're only going to use part of the table. So we know they have a red car. So really the only part that we are interested in is that first row straight across right here. So they have a red car. Now we want to know about the ticket. So that is just equal to 15 people divided by that 150. So 15 people got a speeding ticket out of everybody who had the red car. And in this case, that is 1 out of 10. The second part, we want to know the probability of a red car, but this time the given is that they did get a ticket. So this changes it up. So we're going to use this column instead straight down. So people who did get a speeding ticket, there are 15 that have a red car, but it's only out of 60 people with a ticket. So that is going to be 1 out of 4 of the tickets. This is very different. We're talking about a ticket and a red car. However, the first time we use the group of people with a red car, so 15 out of 150. The second example, we use the group of people who did get a ticket. So how many people had a red car out of those people? Pay very, very close attention to what the given is. This time we use the red car row. This time we use the ticket column. For this example, we are going to use a deck of cards, but we are going to pull 5 cards out of that deck, and we're going to keep the card each time. We want to know the probability that we get all diamonds. So you can write this just as the probability of 5 diamonds, just for a shortcut way of writing it. And we're going to have a first draw, second draw, third draw, fourth draw, and fifth draw. Kind of writing it this way reminds us that the probability is going to change each time because we're keeping those cards. So the first draw, there are 13 diamonds across. You can count them if you wish, and there are 52 cards. Now, because we kept that diamond, there are now only 12 diamonds out of 51 cards. And we're going to keep doing this. We keep a card, so there's 11 out of 50. There are now 10 diamonds left out of 49. And finally, for that fifth one, there are only 9 diamonds left out of 48 cards. Multiplying these straight across with a calculator is how I'm going to do this. If you do this by hand, you can do some cross canceling, but it is a huge number. It's 154,440 on the top, divided by a really huge number. And wait till you see this one. It is a lot of ways you can draw 5 cards out of a deck. And if I put some commons in there, you can see it's 311 million. More than that, almost 312. So on the calculator, you're going to get a funky little answer. It's going to say 4.95198, and you're going to get some more e to the negative 4. That means move that decimal back 4 spaces. So 1 space, 1, 2, 3 more. That means I'm going to have 3 zeros followed by that 495. And I'm going to stop it at that point, but it is really unlikely that you're going to be able to pull 5 diamonds out of a deck of cards like that. For this example, we're only going to draw 2 cards, but we want to know the probability that they are both red. And so this one's kind of a little counterintuitive. We're only drawing 2 cards. It shouldn't be that hard to get this. So we want to know the probability of a red king, given that we already have a red king. And for that first one, there's only 2 of them here. So we have 2 out of 52. But now we've taken away one of those. So we only have 1 red king left and 51 cards. Now I'm just going to go ahead and simplify this just out of habit. So I know it's going to be 1 over, and if you go 26 times 51, that's 1,326. In decimal form, you're going to get that 7.54148. That's rounded e to that -4 again. So approximately 0.00075. And you can put another 4 if you want. So you have like 3 digits in there showing very low probability. For this example, we're going to use a two-way table with the results of a home pregnancy test that was given to 93 women, and then the verification whether or not they were pregnant at a doctor's office. So we want to know for the first one, what is the probability of a woman not being pregnant given that they had a positive test result? This would be considered a false positive. So we're going to go ahead and look down only the column of the positive test. Remember, we look at the second part to figure out what part of the table to look at. There were 5 women that were not pregnant out of 75 women who got a positive test result. Simplifying that, we have 1 over 13. Then for the second one, we want to know what is the probability of a positive test result given that they were not pregnant. So here we're going to use just the row of not pregnant, and that's going across this way. And for a positive test result, we have those 5 women, but that is out of 19 women who were not pregnant, and that doesn't simplify any further. Our final section of this lesson concerns OR probabilities. The probability of either A or B happening, or both, is simply the probability of A plus the probability of B minus that overlap section. If you think back to Venn diagrams, it starts to make sense why we have to subtract out the overlap. And that's to prevent the overlap from occurring more than once in our situation. So if we have a Venn diagram with A and B, if I were to add everything in A and then everything in B, you can see that this overlap region gets counted twice. So what we'll do is just add all of A plus all of B and then subtract out the extra overlap. Mutually exclusive events are a little different. So we consider events mutually exclusive if there is no overlap. So in other words, the probability of A happening and the probability of B cannot both occur at the same time. Since there's no overlap, we can skip this part of subtracting out that extra part and just add the 2 probabilities together. So for this example of OR probability, we're going to go back to the deck of cards, and we want to know what is the probability that we are going to get either a red card or a king. So as long as the card is red, it counts. As long as it is a king, it counts. And if I look at a diagram of red cards and kings and make that into a nice little Venn, we have red cards, we have kings, and there are 2 red kings. There are also 2 kings that are not red cards. Out of the 26 red cards, 24 of them are red. So there's 2 ways we can work this. Since we know the numbers in the Venn diagrams, we can just add them together. 24 plus 2 is 28 out of the original 52 cards. and 4 goes into there 7 times, and 4 goes into there 13. So just slightly more than 50%, which makes sense because we have those extra 2 instead of just the red cards. If I looked at the formula, we have the probability of red plus the probability of a king. And we're going to have to subtract out that probability of a red king, that overlap. And we're going to get the same stuff because all of the red cards, there's 26, plus the kings, there are 4 of those, minus the 2. And if I put this all over 52 cards, you would see I have 26 plus 4 is 30 minus 2, and I get back to that 28 over 52. So whichever way you see it, as a Venn diagram or using the formula, you will get the correct answer. For this one, we're going to go back to the deck of cards, except for this time we want to know what is the probability we get either a queen, and we'll just write this one out in a Venn diagram, and what is the probability of a king. And so there is no overlap in this situation. These are those mutually exclusive events. There are 4 queens, there are 4 kings, and we just are going to add those together. So we get 8 out of 52, and we can divide both of those by 4. We would get 2 out of 13, and that makes sense because each suit, we have 2 out of 13, 2 out of 13, 2 out of 13. Now we have another OR probability, this time working with dice. And the probability is that either the sum of the 2 dice is odd or a 4. Now 4 is even, so there's no way that we can have both odd and even. There is no overlap. So we can think, what is the probability of odd? And we can add that to the probability of a sum of 4. And to get a sum of 4, let's look at those. That's a sum of 4, that's a sum of 4, that's a sum of 4. And 3 and 1, 2 and 2, that's the only way. So there are 3 ways out of 36 different ways to get sums here. Half of the sums are odd. And so just to keep it friendly here, we'll go ahead and make it 18 out of 36, which gives us 21 over 36. Divide each of those by 3, we get 7 out of 12. For this example, we're going to use a two-way table. Notice that the rows, there are 2 options, male and female, but each of the columns now we have 3, A, B, and C. If one student is chosen at random, find the probability that the student was female or got an A. So for the formula, I would need the female, and I'll just use F for female, plus the probability of an A, and they put it in quotes, so I'll do the same. And then we're going to have to subtract that overlap, where it is a female and an A. So females, we're going to read across, there are 25 out of 44. People who got an A, there's 23 out of 44. And if you notice here, if I add those 2 numbers, that's going to be greater than 44, which kind of emphasizes the fact of getting that overlap, which is 13 females who got an A. So if I add this together, I would have 35 out of 44 would satisfy that condition of a female or an A. Another way you can do that when you have a table is you can say, well, here's all of the numbers I need to add up for A's, here's all of the numbers I need to add up for B's, and then out of 44. So you can go 10 plus 13 plus 7 plus 5. And that gives you the 35, and that's still divided by 44. So it matches what we had down here. So decide which way works best for you. Okay, so now this is a you try it. So after I read the problem, pause the video, see if you can figure it out. So we're going to roll the 2 dice. We want to know the probability that the sum of the dice is odd or a single die is 4. So be careful on it. It is not the same problem as before, but pause the video and then come back for a way to work it. Now, since I have a table of values, the first thing I'm going to do is go ahead and I'll circle any of these where the sum is an odd, and that will be half of them. And it does go in a checkerboard pattern. So we have odd, 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 and then we'll go the other way here. So this will give us the half that are odd, and that's 18 out of the 36. But then we can count up all of the ones that I did not circle that have a 4 in it, or I'll just go ahead and circle them. I think it's going to be the easiest way to visualize this problem. So I know I have 18. Here's another 4, so that's going to give me 19. I look through there. There's 20, 21, 22. 23. So I have a total of 23 out of the 36, and that doesn't simplify. Okay, so now we're going to go back and review what we did at the beginning of the lesson, working with the intersection of dependent events. And remember, this time we're going to go back and multiply the probability of the first times the probability of the second. These answers need to be as reduced fractions. So for this, what I'm going to do is simplify everything before I multiply across so I can make sure they're already reduced. Of course, you can use your calculator and just simplify that way. 2 marbles are chosen at random from a jar of 16 marbles without replacement, which means, of course, what happens the second time will depend upon the first event. There are 7 blue marbles, 9 red marbles. What is the probability the first one is red? Well, we start out with 9 red marbles and 16 total. Then the second marble being red, well, there's now only 8 left out of 15. And again, I want to simplify these before I multiply. So 3 goes into 9 3 times, and it goes into 15 5 times. 8 goes into 8 once and twice into 16, and that's going to give me 3 out of 10, and that's in simplest form. For the next problem, 2 cards are drawn at random without replacing. What is the probability that the first card is a heart? Well, 1 out of 4 cards, if I simplify, is a heart. What is the probability the second one is a black card? Well, we have 26 black cards, but we've taken 1, so we only have 51 left. And now I'm going to go ahead and simplify those, because 4 is an even number, so I'm going to go ahead and cut that in half and cut this one in half, which gives me 13 out of 102. For the third problem, 2 letters are chosen at random to form a password. The letters must be different. Find the probability the first letter is a consonant and the second is an I. So I'm going to start out, I have 26 letters, and then after I draw one, I'll have 25 left. Now, a consonant is not a vowel, so this is kind of thinking of the complement here. So I have A, E, I, O, and U would count as my vowels. So if I have 5 vowels and 26 letters, 21 are going to be consonants. For the second letter being an I, there's only 1 of those. So now if I look at this, 21, that's 3 times 7, 26, that's 2 times 13, this is 5. So actually this is going to be simplified if I multiply straight across. And then we get 650 on the bottom. Whoops, my numbers aren't writing. I apologize for that. Okay, and now we have our last one. We have a jar with 42 assorted coins in them. And it says we have 11 pennies, 10 nickels, 12 dimes, 9 quarters. 2 cards are chosen at random without replacement. The probability of the first being a nickel would be 10 out of those 42 coins. And the probability that, I think I said the second on this one, but the probability of the first coin is a nickel times the probability of the second being a penny, that would be 11 out of only 41 left. Again, I can simplify this to make my math a little bit easier, and that's even, so that's going to be 5 over 21, and multiplying that across gives me 55 over 431. Okay, so a little review there for you. And now we have our last. Okay, for this problem, we're going to compare the idea of an and or an or. If you would like to pause this video and then try it first on your own and then come back, that would be a really good idea. So we have a table. We're back to that red car and speeding ticket. Different numbers, remember they're randomly generated. So we want to know first the probability somebody has a red car and got a speeding ticket. Now what's really cool about a two-way table is we can see the answer right here. It's 15 of those people out of the 665. So we're going to go 15 out of 665, and both of those are divisible by 5. 5 goes into the 15 3 times. 5 goes into 665 133 times. So there's our answer for that one. Depending upon how they want it, for more, they may want you to divide that out and get the decimal. In that case, you wouldn't need to simplify first. For the next one, since we have a two-way table, there's 2 ways to do this, but we want a red car or a speeding ticket. So we can do the totals, and we have 60 out of 665 that have that speeding ticket, and we have 150 out of the 665 that have a red car, and we could subtract the 15 that have, we've just counted twice, that have a red car and a speeding ticket. So that is option 1, and that's going to give us 195 out of 665. Both of these again are divisible by 5, and 5 goes into there 39 times. 5 goes into 665 133. Now, the other thing I could have done is just said, well, speeding ticket or red car, and notice if I have added together these values, I would have also gotten the same thing. So 6, 7, 8, 9, 1, and it's the same. That's that 195. So 2 ways to do it. If they've given you those values, you can just count up what you want, or you can do the totals and subtract out. So that's the end of this lesson. Remember, you can look back at it as you're working on your homework and quiz and your media or mini lessons, and I will see you after the break.